Hey, you ever look at a scattered collection of things like a messy desk or maybe just a random list of ideas and wonder how a computer could possibly make sense of it all if it's not in some perfect step-by-step order?
That's a fantastic way to jump into a really intriguing problem in artificial intelligence.
Right.
Today, we're going to take a deep dive into how AI handles information when the order doesn't inherently matter. Our roadmap for this is a fascinating research paper from Google Brain called Order Matters, Sequence to Sequence for Sets.
Order matters
For sets.
for sets. That almost sounds like a contradiction, doesn't it? I mean,
Yes.
the whole point of a set is that the order doesn't change what it is.
Exactly.
So what's the central head scratcher this paper is trying to, unravel?
Precisely that paradox.
Hmm.
The paper dives into how the order in which we feed information into AI models, and interestingly, even the order we expect them to output things, dramatically affects their ability to learn. It specifically looks at where the usual sequence-to-sequence methods, which, work wonders for ordered stuff like language, where they kind of fall short when we're dealing with these unordered collections.
Okay, so we're moving beyond just predicting the next word in a sentence here. What kinds of, real-world problems bump up against this unordered data challenge?
Oh, lots of things. Think about sorting a bunch of numbers. The final sorted list, it's the same no matter how jumbled the input was, right? Or imagine an AI trying to spot all the different objects in a picture. Does it see the cat first or the dog? It shouldn't change the fact that both are there.
Yeah, makes sense.
Even in language, sometimes the core meaning isn't strictly tied to the exact word sequence. The paper touches on all these kind of scenarios.
Okay, so our mission today, as the title kind of hints, is to figure out why this idea of order seems to be such a big deal for AI, even when, logically, maybe it shouldn't be. And maybe more importantly, how smart people are inventing new ways for AI to handle this kind of unordered information more effectively. I hear there are some surprising twists, so let's get into it.
Absolutely. Let's maybe kick things off by talking about the workhorse behind a lot of modern AI,
Yeah.
the sequence to sequence or SIC to sec framework.
Yes, sick to sec.
This has been a real game changer in areas like machine translation, where you've got, say, a sentence in one language that's your input sequence, and you want its translation in another, the output sequence.
Right, and as the paper points out, a key part of how these models work is something called the chain rule for probabilities.
Mm-hmm.
It's basically a way of calculating the likelihood of a whole sequence by looking at the probability of each item in it, given everything that came before.
Precisely. And that's a very natural fit for sequential data. But the core question this paper raises is, what happens when either what we're feeding in or maybe what we want to get out isn't really a sequence in the first place?
Like the sorting example.
Exactly. Let's say we have a set of numbers. We want the AI to sort them. Does the random order we initially give those numbers to a standard seq2sec model actually matter? You'd think. Probably not.
And yet, the paper throws out some really compelling examples where order makes a, surprisingly big difference. Let's maybe dive into a couple of those. Machine translation seems like a good place to start.
Yeah, this one's really eye-opening. Researchers found that simply reversing the order of an English sentence before feeding it into the translation model, it could actually lead to a noticeable jump in the quality of the French translation.
Wait, hold on. Just reading the sentence backward made the translation better.
They saw, I think it was a 5.0 increase in the BLU score.
It's mind-bending. All right.
Right.
Reversing the input shouldn't fundamentally change the meaning, so why would it lead to better translations? This really underscores the unexpected ways order impacts these models.
It really does.
And for anyone not familiar, that BLEU score is a standard way we measure machine translation quality. And yeah, a 5-point jump is pretty significant.
Very significant. The researchers think this might be connected to how neural networks actually learn. The training process isn't always a straight path. It's what they call a non-convex optimization landscape.
Okay.
Think of it like trying to find the lowest point in a really bumpy valley, starting from a different spot, or maybe presenting the data in a different order might actually help the model find a deeper, better valley, a better solution.
And it wasn't just translation where they saw this effect, was it? The paper also talks about constituency parsing.
Correct. Constituency parsing, which is all about breaking down a sentence into its grammatical parts, like noun phrases, verb phrases.
Gotcha.
In that case, too, just reversing the input sentence led to a clear improvement in how accurately the model could parse it. It's another example where a seemingly superficial change in input order had a real positive impact on performance.
And then there's the convex Hull computation, Figuring out the smallest shape that can enclose a set of points. This one feels like it makes a bit more intuitive sense, maybe, how order could play a role.
Absolutely. If you take that jumble of points and sort them first, maybe based on their angle, before you feed them into the model, the paper points out that the task becomes computationally much easier.
Okay.
And not surprisingly, the AI models trained on this pre-processed ordered data were faster to train and achieved significantly better accuracy. I think he was up to a 10% absolute increase in some cases.
Wow. So the big takeaway from all these examples is, well, even when we're dealing with information that isn't inherently sequential, the way we order or present that info to the AI can have surprisingly large effect
A huge effect.
on how well it learns, how well it performs. It seems the learning process itself in these neural networks is quite sensitive to input order.
Precisely. And this brings us nicely to the challenge of dealing with true input sets, where there's just no natural order at all. How do we teach an AI to understand a collection of items when the order just shouldn't matter?
Right. The paper contrasts this with, like, simple bag-of-words approaches.
Yeah, bag of words is where you basically just count how many times each item appears. You completely lose any info about how they relate or the original order.
It's order invariant, sure, but it feels, well, maybe too simplistic for a lot of tasks.
It often is. And the paper highlights another limitation. Bag of words often leads to a fixed size representation no matter how many items are in your input set.
Ah.
So it's probably not going to scale well for really large collections. The model just wouldn't have enough sort of memory bandwidth to capture everything.
So the researchers at Google Brain came up with a more sophisticated way to handle these input sets. The read, process, write model.
Yeah.
That sounds interesting. How does that work?
Okay, so the big idea here is to feed in that jumbled mess of information and have the AI understand it without caring about the initial order. That's a huge step forward.
Definitely.
This architecture is specifically designed to process input sets in a way that doesn't depend on the order. It's got, like you said, three main parts: read, process, and write.
Okay, let's start with the read block. What's its job?
So the read block takes each individual item from the input set and uses a small neural network to turn it into a representation, like a memory vector. And importantly, it uses the exact same neural network for every single item in the set.
The same network for each item.
Okay. Yeah. So what you end up with is a collection of these memory vectors, one for each thing in our original jumbled set, sitting in a kind of memory bank.
Got it. So we've taken our unordered set and turned it into a set of these vector representations. What happens next in the process block?
The process block is where the magic of dealing with the unordered nature really happens. It uses an LSTM. That's a type of recurrent neural network.
Right. LSTMs are usually sequential.
They are. But here, the LSTM doesn't directly get any new external input like usual. Instead, it goes through multiple processing steps. And in each step, it looks at those memory vectors we created in the read block.
How does it look at them?
It uses something called an attention mechanism.
Attention. That keeps popping up everywhere in AI lately. How does it help here ignore the original order?
Well, the attention mechanism lets the model selectively focus on different parts of the memory vectors during each processing step. Think of it like the model being able to, zoom in on different aspects of the input set as needed.
Okay.
And crucially, because this focusing is based on the content of the memory vectors themselves, not their position, the final output of this process block stays the same even if you completely shuffle the order of those initial memory vectors.
I see.
The LSTM's internal state gets updated based on what it pays attention to, but the overall processing isn't tied to any specific sequence.
That makes perfect sense.
Yeah.
The model can learn how the different pieces of info relate without being biased by the arbitrary order they came in. Brilliant. Now, how does the write block take this processed info and generate the output?
The write block uses what's called a pointer network.
Pointer network.
Yeah, imagine the model has this collection of processed information in its memory, right, from the process block. Its job is now to sort of point to items in that memory, one by one, to create the output sequence. So in their sorting experiment, for example, the pointer network would learn to point to the representation of the smallest number first, then the next smallest, and so on, building the sorted list step by step.
And the paper mentions an extra glimpse mechanism in there, too, in the right block. What does that do?
The glimpse is basically another little look, another attention step that happens right before the model decides which element to point to next.
Okay.
It lets the model take another quick scan of the processed memory, maybe focusing on what hasn't been picked yet, to help it make a better choice for the next item in the output sequence, like a little double check.
Got it. So to see how well this whole read, process, write thing actually worked for sets, they tested it on sorting random numbers, you said. How did it compare to just like a standard C2SEC model?
Yeah, they compared it to a basic C2SEC model where the jumbled set of numbers was just fed into an LSTM one after the other, the standard way. The results were quite revealing.
How so?
When the read, process, write model had 0 processing steps, basically just read and write, it actually did a little worse than the regular LSTM.
Oh, sure.
But as soon as they gave it even 1 processing step, its performance started to get better. And with more processing steps, it significantly outperformed the vanilla C2SEC model, especially when they had more numbers to sort, like 50 instead of 5.
That really highlights the advantage of that order-independent processing, doesn't it?
Absolutely.
It scales much better for larger, unordered inputs compared to just forcing them into a sequential mold. And you mentioned those glimpses in the right block. They help too.
Yes, those extra little attention steps right before selecting the output element gave a nice accuracy boost to both models, the baseline C2SEC and their new read, process, write one.
Interesting.
It just reinforces the idea that strategically focusing on the relevant parts of the information is really key for these kinds of tasks.
Okay, so we've tackled handling unordered inputs. Now, the paper shifts gears a bit and looks at the challenges of generating sets or structured data as output. Because even if the final thing we want is, say, a set where order doesn't matter, the actual process of creating it often involves making decisions one step at a time, right? In a sequence.
That's a really critical point. Well, the math, the chain rule, lets us think about the probability of a whole set of things in any order. The practical reality is that the specific order we choose when our AI models generate an output sequence can really impact how well they learn, especially for models like LSTM.
So the output order matters too.
Yeah.
The paper brings up language modeling again here, right? Even though a sentence is a sequence, they played around with training models on text where the word order was messed with.
They did. They looked at the natural order, the reversed order, and even a scrambled order where they reversed every group of 3 words.
Weird. What did they find?
Interestingly, the model trained on the completely reversed text did just as well as the one trained on the original order in terms of predicting the next word.
Same as the input finding for translation.
Exactly. But the model trained on that nonsensical scrambled order, its performance did get worse. And it seemed to have a harder time during training, too. So it suggests that while LSTMs are pretty flexible, really disruptive orderings can still hinder learning.
And the parsing example is also fascinating here, showing how different ways of turning a tree structure into a linear sequence can affect learning.
Yeah, that was really cool. They compared generating a parse tree by traversing it depth first versus breadth first.
Okay, different ways to walk the tree.
Exactly. Even though both sequences perfectly capture the same tree structure, the model trained to produce the depth first sequence did much better. It got a higher score, and it was more likely to actually produce a valid tree structure at the end.
And the breadth first.
That seemed much harder for the model to learn. It struggled more.
So this really highlights how the choice of output order can introduce biases or just make it harder for the model to grasp the underlying structure, even if the final output represents the same thing.
Absolutely. And this becomes even more critical when we think about combinatorial problems. Things like sorting or the traveling salesman problem.
Right, where there can be tons of equally valid output sequences.
Exactly. If you're trying to get a model to output a sorted list, say, and you don't tell it always output in increasing order, it basically has to learn that every possible permutation of the sorted numbers is a correct answer.
That sounds incredibly inefficient, like it's diluting the learning signal.
It really is. The paper mentions that in their earlier work on these kinds of problems, trying to constrain the output format as much as possible was key.
How so?
Like for the traveling salesman, maybe always starting the route from the lowest index city and always going, say, counterclockwise. Things like that led to significant speed-ups in learning and just better overall results.
So enforcing a canonical order helps a lot. But what if we don't know the best canonical order? Or what if there isn't one?
Right. The ideal situation would be for the model to not only handle unordered inputs, but also to figure out the best order for generating its outputs itself.
And the paper proposes a way to do just that, to let the model actually learn the optimal output order during training.
Yes. This is a really clever idea, I think. Instead of us having to guess or manually design a specific output order, the model gets to explore different orderings and learn which ones make the task easier, which ones lead to better results.
How does that work in practice? I mean, trying out all the possible orderings sounds,
Mm.
well, computationally impossible for anything but really short outputs, right?
Uh,
And Factorial grows incredibly fast.
You're absolutely right. That's the major hurdle. The paper acknowledges this. Their initial thought, just trying to maximize the probability across all possible permutations,
Yeah.
yeah, not feasible for any reasonable output size.
So what's the trick?
They came up with a more practical approach. It involves a pre-training phase, followed by a smarter way of choosing which orders to actually try during the main training.
Okay, tell me about this pre-training phase. What's the goal there?
During pre-training, the model is basically shown examples where the correct output set is presented in lots of different random orders.
Ah.
It's like saying, look, this is the right set of things, but we're showing it to you in all sorts of different sequences. This helps the model become more robust, less brittle, when it sees different output sequences that represent the same underlying structure.
Okay, so it gets used to the idea that order can vary, and then comes the clever way of choosing which orders to try later.
Exactly. After this initial pre-training, instead of just randomly sampling orders or trying everything, the model starts to sample orderings based on how likely they seem according to what it's learned so far.
So it uses its own predictions to guide the sampling.
Kind of, yeah. It's essentially trying to generate the output in an order that it thinks makes the most sense, given its current understanding of the task. The key is they use a technique called ancestral sampling, which is a very efficient way to generate a sequence step by step based on the model's learned probabilities.
Okay, clever. And the paper uses a 5-gram language modeling experiment to show this works. Remind us what a 5-gram is.
Sure, a 5-gram is just a sequence of 5 words, like the cat said on the...
Got it. So how do they apply this learning of output order to that task?
Well, they treated each 5-gram as a set, but they cleverly included the original position of each word as part of the element.
Oh, okay. So even if you shuffle the words, you still know where they originally came from.
Exactly. Then they trained a model to predict these 5-word sets. First, they tried always showing them in their original natural order. Then they tried showing them in a completely jumbled order. And finally, they used their new method to let the model learn which order to use during training.
Oh, what happened? Did the model actually figure out a good output order on its own?
It did. So the model trained on the fixed natural order performed better than the one trained on the jumbled order, which just confirms again that output order really does matter.
Right.
But here's the cool part. When they let the model learn the order, using that pre-training and sampling approach on data containing lots of different permutations, it eventually settled on generating orderings that were very close to the original natural order, or sometimes its reverse. And it achieved the same high level of performance as the model trained only on the natural order.
That's a really exciting result. It shows the model can automatically discover these beneficial output orderings without us needing to bake them in beforehand.
Exactly. No explicit prior knowledge needed about what a good order is.
So let's try and bring it all together. Our deep dive into this really fascinating paper has shown us pretty clearly that order, well, it really does matter for AI models, even when we're dealing with data that at its core seems unordered.
Yeah, it's kind of counterintuitive at first, but the evidence is strong.
And it seems like this is largely because of, well, how these models actually learn that bumpy optimization landscape and how they represent information internally.
Precisely. And the paper makes 2 really significant contributions here, I think. First, it gives us that read, process, write architecture with those crucial attention mechanisms.
Right, the order invariant input processing.
Exactly, a principled way to handle input sets without being thrown off by the element order. And second, it introduces this clever training method that allows models to figure out effective output orderings for themselves.
Instead of us having to guess or rely on predefined, maybe suboptimal sequences, it's pretty mind-blowing, really, to think about how these findings could lead to more powerful, more efficient AI systems. Systems that can truly understand and generate complex, unordered information.
It opens up a lot of possibilities.
It really makes you wonder, if we can get AI to learn the natural or maybe the optimal order of information in different domains, what new possibilities could that unlock? especially in fields where maybe we don't even fully understand the best underlying structure yet?
That's a fantastic question.
Could AI actually help us discover hidden relationships, optimal sequences in all sorts of complex systems we haven't even considered?
That's a really thought-provoking point to end on. It gets to the heart of why this kind of research is potentially so transformative, doesn't it? It suggests AI might become a tool not just for processing information as we currently structure it, but maybe for uncovering fundamental structures and relationships that are hidden from us right now.
Absolutely fascinating. This has been a truly eye-opening deep dive. If you, the listener, are as intrigued as I am, I definitely recommend checking out the original research paper. Again, it's called Order Matters: Sequence to Sequence for Sets. It's packed with even more detail, graph specifics, really worth a look.
Definitely.
Thanks so much for joining us on this exploration today.